All right, here is the video for note 6-2, expected value. So let's consider this situation. Billy Bob asks his parents for money. Instead of giving Billy Bob money, his dad offers to flip a coin. If the coin lands heads, he wins, and his dad will give him $20. If the coin lands tails, he will receive nothing. Billy Bob is skeptical, so he goes to his mom and asks for money. Instead of giving Billy Bob money, his mom makes a different offer. She will roll a die and give $3 for every spot that turns up. Meaning if she rolls a 1, she'll give $3. If she rolls a 2, she'll give $6, etc. What's the better offer? So what we're going to learn in this lesson is how to determine which of these two situations is a better offer. Okay, so in class we did a little simulation, which we're just going to skip for the sake of this video. All right, so let's talk about the mean of a random variable. So the mean is also called the expected value, which is like a weighted average, just like your grade. We use the Greek symbol mu, or mu of x, if we're talking about the mean of a random variable x. Generally, I'll just write expected value of ex. To find the mean or expected value of x, what we do is we multiply each possible value of x by its probability, and then we add the product. So if this is our probability table, we would multiply x1 times p1 plus x2 times p2 plus x3 times p3 all the way to the end, and that would be our expected value. All right, so let's look at an example. Suppose that we're playing the lottery and we choose a 3-digit number. If the lottery shows our same number, we win $500. There are 1,000 possible digit numbers, so the way that we can figure that out, we can use a multiplication rule, right? This is a 3-digit number, and assuming that we can choose 0 as a number, there's 10 different options we can choose for the first number, 0 through 9. There's 10 different options for the second, 10 different options for the third, and if we multiply all of those, that gives us the 1,000 different possible digits. Okay, so in terms of your chances of winning, if there's 1,000 possible digits and you're choosing one single number, your chances of winning is 1 in 1,000. Which means your chances of losing would be 999 over 1,000. So now what we could do is we can fill out this expected value table to determine what is our average profit from many tickets or our expected value. Well, we know that if we win $500. So we're going to assume we're not paying any money to play this game. So we win $500, which means our profit is going to be $500. If we lose, we win nothing. So our profit would be $0. Then we have to figure out the probability of each thing. So the probability of winning, we know is 1 out of 1,000. And we know the probability of losing is 999 over 1,000. So this right here is basically like what we did yesterday. We have our random variable, which is our profit, and we have our probability of each different situation. So to calculate the average profit from many tickets, that's the expected value. What we do is we take our profit and we're going to multiply that by the probability. So it's going to be 0 times 999 over 1,000 plus our other outcome times the probability. So now we're going to use a calculator. So to put that in our calculator, we would do 0 times 999 over 1,000 plus 5 times, or 500 times 1 over 1,000, and we would get an expected value of 0.5. So 0.5. So what that means is if we play this game many times, we would win about 50 cents per game on average. Okay, because the way you have to think about it is sometimes when we play, we're going to win $0, and very rarely when we play, we're going to win $500. If we were to take the average and add up all the zeros and the 500s, it would average to be about 50 cents per game. Okay, so now let's consider the case where we actually pay $1 to play. Let's see how that's going to change. Well, in terms of the probability is going to stay the same. The probability of winning still is going to be 1 over 1,000. The probability of losing is still going to be 999 over 1,000. But now our profit is going to change. If we're paying $1 to play, we need to subtract that amount from each of these profits. So when we win, we're not actually going to win $500. We're actually only going to win $499 because we paid $1 to play. And when we lose, we're not just going to lose $0. We're going to lose the $1 that we spent to play. So the expected value in this case is going to change. So it's going to be -1 times 0.999 or 999 over 1,000 plus 499 over 0.001. So in this case, our expected value is going to be -0.5. So we would say if we were to play this game many times, we would lose on average 50 cents per game. So the reason in this case we're saying we lose is because our expected value is negative. All right, so let's go back to the mom and dad's offer from the beginning of the lesson. So remember in this case, mom's offer was if you roll, for every number that you roll on a dice, you earn 3 times the amount of dollars. So for instance, if you roll a 1, you would win $3. If you roll a 2, you would win 6, 3, 9, 12, 15, and 18. And we know the probability of rolling any single number on a dice is 1 out of 6. So each of these probabilities is the same. For dad's offer, what it was is if you roll heads, you get $20. And if you roll tails, you win nothing. And we know the probability of rolling heads is 1/2. The probability of rolling tails is 1/2. So now that we know how to calculate the expected value, we can calculate the expected value of each situation and figure out what is a better deal. So remember, to calculate expected value, take the profit and multiply that by the probability. And since mom and dad aren't charging us to pay to play, we don't have to take that into account. All right, so to calculate this expected value, we're going to put this into our calculator, which I'm going to do. So for mom's situation, we do 3 times 1, 6, plus 6 times 1, 6, etc., etc. So the expected value in that case would be $10.50. And then we're going to calculate the expected value of dad's offer. So in this case, it's 20 times 1/2 plus 0 times 1/2. Well, this one, it's pretty easy to do in our head. We know 0 times 1/2 is just 0. 20 times 1/2 would just be 10. So the expected value in this case would be 10. So by looking at the expected values, we can see that the expected value for mom's offer is better. So mom's offer is a better deal. So the way to interpret this in context, we would say if we were to play mom's game many times, we would win on average $10.50 per game, whereas dad's offer, if we played this game many times, we would win only $10 per game. All right, so let's look at another example. So in this problem, it says you pay $1 to play my game. We're going to flip a coin. If all 3 coins are the same, you get $3. Otherwise, basically, you get nothing. So what is your expected winnings? Remember, we did this table yesterday. The probability of no heads is 1/8. 1 heads would be 3 out of 8. 2 heads is 3 out of 8. And all heads would be 1 out of 8. So now in each situation, we do have to take into account we're paying $1 to play. So we know we need to be subtracting 1 from the profit. Okay, well, the only case where we make a profit is if all 3 are the same. So all 3 are the same for all heads or no heads. And all 3 are the same if we get all heads. Okay, but since we're paying $1 to play, we know we need to subtract 1. So our real profit is going to be $2 in both cases. And if we get 1 head, we get $0. But in that case, we would be losing $1, so it'd be -1. So to calculate the expected value, we're going to do 2 times 1/8 minus 1 times 3/8 minus 1 times 3/8 plus 2 times 1/8. So the expected value in this case is going to be negative 0.25. So we're going to say if we played this game many times, we would lose, on average, 25 cents per game. So again, the reason why we're saying we lose is because our expected value is negative. All right, here's another example. It says you pay $1 to play my game. A fair six-sided die is tossed. You win $2 if the result is a 1. You win $1 if the result is a 6, but otherwise you lose $1. So there's actually two ways you can make this table. You can make it where you list out every single outcome, rolling a 1, 2, 3, 4, 5, or 6. And in case, let's see, what they give us is that you win $2 if the result is a 1. You win $1 if the result is a 6. Otherwise, you lose $1. Okay, but in this case, we do need to subtract the amount that we're paying to play. So 2 minus 1 is 1. We already say we lose $1 here. And then 1 minus 1 is 0. That's where the 0 comes from. So you could do it that way. Or what you can do is you can combine outcomes. Since these 4 situations have the same outcome, we can just combine them into one. We roll a 2 or a 5. Your profit would be negative 1. And the probability of that happening, we can add those together, which would be 4 out of 6. And each of these would be 1 out of 6. This one a little bit easier to put in your calculator because you can end up just doing, for the expected value, it's going to be 1 times 1/6 plus 0 times 1/6 minus 1 times 4/6. This is a little bit more to put in your calculator. So the expected value in this case is negative 0.5. So to interpret this expected value in context, which I'm just going to say verbally, if we were to play this game many times, we would lose on average 50 cents per game. All right, here's another example. So it says a local club plans to spend $10,000 to host a baseball game. They expect to sell tickets worth a total of $15,000. But if it rains on the day of the game, they won't sell any tickets and the club will lose all the money invested. If the weather forecast for the day is 20% possibility of rain, is this a good investment? So there's kind of only two outcomes here. It's either going to rain or it doesn't rain. We know the probability of it raining is 20%, which means the probability that it doesn't rain is 80%. Well, we know if it doesn't rain, they are going to sell tickets worth $15,000. However, remember that they invested $10,000. So in that case, their total profit is only going to be $5,000. And if it rains, they lose all the money they invested. Well, in this case, they invested $10,000. So they would lose $10,000 if it rained. So that would be the profit for raining. So then the expected value is going to be negative 10,000 times 0.20 plus 5,000 times 0.80. And we put that in our calculator. I'm not going to show the calculator just to make it a little easier. You should get $2,000. So in this case, we're not going to say if we play this game many times because this isn't a game. We would say, yes, this is a good investment. Because the expected value is positive. All right, here's the last example here. So you pay $2 to play my game. You spin the spinner, and whatever region it lands on, you win. What is the expected value for this game? All right, so here's our spinner over here. And we see it's divided into these sections. You can land on a 0, you can land on a 1, you can land on a 2, or you can land on a 10. So in terms of the profit, well, you get whatever you land on. However, we do have to take into account that we are paying $2 to play. So we're going to subtract that from each of these amounts. So if you land on the 0, you're actually going to lose $2. If you land on the 1, you get $1 back that you paid, but you're still going to end up losing 1 since you paid $2 to play. If you land on the 2, your profit's actually going to be 0. You break even. And if you land on the 10, your profit is going to be 8. So in terms of the probability, we have to take into account the different sides of each shape. Well, if we look at the 0, there's 2 quarter sections, so that's going to be a probability of 1/2. If we land on the 1, that is going to be 1/8. The 2 is going to be 1/4. And the 10 is going to be 1/8. So what we could do just to make sure if we add these all together, they should all equal to 1. What you could also do is kind of cut these so they're all in eighths, so every shape is the same. So then we can think of rolling a 0 as actually 4/8. Rolling a 1 is 1/8. Rolling a 2 is 2/8, or yeah, 2/8. And 1/8, that might be a little bit easier to see. Okay, so now to calculate the expected value, we're going to multiply the profit times the probability. And we're going to put that in our calculator. And when we put that in our calculator, we get an expected value of negative 0.125. So to interpret that in context, we would say if we played this game many times, we would lose on average about 13 cents per game.